Hello everyone, and welcome back to some more remote learning. In today's example video, we're going to do some more problems on optimization. So now that we finally understand what the relative max and mins of a function are, we can use that same strategy to find those critical points to also find the optimal solution of real-world functions. Because think about those maxes and mins. They're found by using the derivative of the function and setting it equal to 0. So once we get those critical points, we will know the maximum and minimum values of our original function. So if we had some equation in the real world where we wanted to find the maximum value that we could possibly have or the minimum value we could possibly have, we would do the same. We could take the derivative, set it equal to 0, and solve, applying it in the real world. Now, there's a couple steps that I find helpful to use to solve optimization problems. One of the first ones is to draw and label a picture with given variables if it's applicable. Once you can visualize what you're trying to optimize, it may be easier to write your formulas because that's the next step. You're going to identify the objective. So the objective function is usually the function that you're trying to either find the maximum or find the minimum value of. For the objective function, we're eventually going to take the derivative. But not only do we need to identify an objective function, we need to identify any constraints. And then once we identify those constraints, we're going to attempt to write the objective function in terms of one variable. We don't want to do this like we did in related rates where we took the derivative with respect to time and then we had implicit differentiation throughout our problem. No, we want to have just some function in terms of a single variable so that when we take the derivative, we can easily set it equal to 0 and solve. So after we write the objective function in terms of that single variable, we'll move on to step 4 where we're going to find the minimum or maximum of that newly adjusted objective function. And then finally in step 5, we're going to use that value that we got, that calculated value, and substitute it in to find the information we want. Sometimes we'll want to know the maximum volume, whereas sometimes we want to know those actual dimensions once the volume is maximized. So we just want to make sure we use that calculated value appropriately to find the correct solution. So let's dive into example 1, giving this a little bit of practice. So in example 1, it says a rectangular pen is being constructed for chickens. One side of the pen will be against the barn and not require any fencing. We're going to determine the dimensions that will maximize the area for the given amount of fence. So it looks like there's a part A and a part B. One of them, the total amount of fence we're allowed to use is 50 feet, and the other, the total amount is 75 feet. But the picture is roughly going to be the same for each. It's just the constraint that's going to be changing. In part A, our constraint is that we only have 50 feet total. Whereas in part B, our constraint is that we have 75 feet total. So let's go ahead and draw our picture. So here I have some barn that the fence is going to be up against, and it's a rectangular pen that we're trying to form. So my fence is only on 3 sides. And then you can see I drew a couple chickens in there. Not the best artist, but there we go. There's our barn. That's the fence we're trying to draw. And our constraint is that we only have 50 feet. Well, eventually we're going to want to add up those sides of the fence. So the 2 sides of the fence that are parallel, I'm going to write each of those as X. Those will be the same size because it's a rectangular pen. And then this other side is just going to be Y. And we don't have to worry about fencing over here because we're up against the barn. So now I've drawn my picture and I've labeled some variables within my picture so that I can visualize it. Step 2, we're going to identify our objectives and our constraints. So our objective function is what we're trying to either maximize or minimize. And it says determine the dimensions that will maximize the area for the pen. So our objective function is going to be the area. And what is the area of this rectangular pen that we have here? That area is, I'll write my objective function in green. That area is equal to X times Y. So our objective function is X times Y. Area equals X times Y. Eventually, we're going to take the derivative of that and set it equal to 0 to find that maximum area. However, in order to take the derivative for optimization problems, I only want one variable in here. So I'm going to use my constraint to rewrite it. And what's my constraint? The total amount of fencing I can have is 50 feet of fencing. So my constraint is that 50 feet is going to be equal to, my fence is x plus y. That's my perimeter. So 2x plus y is my constraint. All right, so now I've got my objective function, I've got my constraint, but I want to, in step 3, write the objective function as a single variable. And as of now, my objective function contains both an x and a y. Because I'm trying to maximize that area, I want to leave area so that I can take the derivative with respect to one variable. So I have x and y, which means I can manipulate my constraint equation, which has two variables, to write that in terms of one variable. So I'll just go ahead and solve for y. So I'll get that y is equal to 50 minus 2x. So now when I go to write my area, my objective function, that's going to be x times y, which y is 50 minus 2x. And there we go. We have my objective function, our objective function, in terms of one single variable. So we're going to find the maximum or minimum of that objective function, and we're going to be taking the derivative. But before we take the derivative and set it equal to 0, why don't we just simplify this down a bit? Area is going to equal, distributing my x through, that's going to be 50x minus 2x squared. So now I'm going to take the derivative of area with respect to x. So if area is a function of x, a of x, I'm going to find a prime of x. And a prime of x, or a prime, is going to be, well, derivative of 50x minus 2x squared is going to be 50 minus 4x. Now that I've found the derivative of my objective function, I'm going to set it equal to 0 to find when it's at a minimum or a maximum. So when I set this equal to 0, I'll get that 50 is equal to 4x. And when I divide both sides by 4, I'll get that 50 over 4, or about 12.5, is equal to x. So x is 12.5, and that's going to give me a maximum area. Now, how do we know it's a maximum and not a minimum? Because setting the derivative equal to 0 is for finding our critical points, and our critical points can be either maxes or mins. We've learned about the second derivative at this point in time. If that second derivative is negative, that means we're concave down. And if we're concave down, we have a maximum. If our second derivative is positive, that means we have a minimum. But if we look at this and take this second derivative, we're going to get a negative 4, concave down, we're at a maximum. So we're all set. Now, 12.5 feet for x isn't my final solution because I want to determine the dimensions. So now I'm going to use my calculated value I just got, that 12.5x, in order to obtain my answer. So I know that the two parallel sides of my fence are 12.5 feet, but I don't know what y is. But remember, our relationship that related y and x together, well, we have that area formula, but we don't exactly know what the area is, we just know that it's maximized. Let's use our constraint equation, and better yet, let's use the one where we've already solved for y in terms of x. So I'm going to get that y is going to be equal to 50 minus 2 times 12.5. 2 times 12.5 is going to be 25, so y is going to be equal to 50 minus 25, which is 25 feet. So, filling in my dimensions now, the two parallel sides are 12.5 feet, and the single side is 25 feet. 2 times 12.5 plus 25 is going to give us that fencing we can use, which is 50 feet. So if I have 12.5 for both my sides and 25 feet, I could also ask what actually is that maximum area that we calculated. And that would be plugging 12.5 and 25 back in for my area. So for 50 feet of fencing, my maximum area is going to be 12.5 times 25, which is 312.5 feet squared. So we're going to do the same exact problem, except now our total amount of fencing is 75 feet. Our objective function isn't going to change, just our constraint. So the process remains the same. Is area equals x times y. We're using that same exact picture because everything else is the same except the amount of fencing we're allowed to use. So now my constraint is 75 equals 2x plus y. That total perimeter of fencing, x plus y, is going to add up to 75 feet because that's my total amount of fencing I have to use. Remember, our next step, we want to maximize that area, so we're going to take the derivative. But before we take the derivative, we only want it in terms of one variable. Manipulate the constraint to plug the variable into our objective function. So we're going to have that y is equal to 75 minus 2x. And again, if I wanted to, I could solve for x here and use that. It's just a little messier because then we're going to be dealing with a fraction when we go to plug everything in. So I just want to leave it as y equals 75 minus 2x. We're ready to go ahead and plug that into our objective function. So area is going to equal x times 75 minus 2x. That's going to be area equals 75x minus 2x squared. Now we're ready to take the derivative a prime or a prime of x because we have a as a function of our single variable x. That's going to give us 75 minus 4x. Again, when we set this equal to 0, we're going to get a maximum value because our second derivative is a negative, so we know that we're concave down, which is going to relate to a critical point that's a maximum. Now solving this, I'll get that 75 is equal to 4x, so I'll divide both sides by 4 to get about 18.75 feet of fence. So 18.75 feet is one side, which correlates to technically two sides because I have 2x, but now I'm going to plug that in to solve for my missing side y because I want the dimensions that will maximize the area. So y is going to be equal to 75 minus 2 times 18.75, which is going to give me 37.5 feet. So my dimensions are that the two parallel sides are 18.75 feet and that other side that's parallel with the barn is 37.5 feet. And if I wanted to know my maximum area, I could have asked that, and then we just take that x value and multiply it by y to get roughly 703 feet squared. Let's move on to our next optimization problem. In our next optimization problem, it says identify two positive numbers that sum together to equal 100 and have a maximum product. So this one doesn't really require a picture, it's not applicable in this case, but we can write our objective function and our constraint. Our objective function is that we have a maximum product between those two numbers. We don't know what those two positive numbers are, so I'm just going to say that some maximum product, I'll write P for the product, equals x times y. Now our constraint tells us that x and y, those two positive numbers, sum together to equal 100. So I know that x plus y equals 100. And if I want to maximize my objective function, which is now in terms of two variables, I need to use my constraint to solve for one variable so that my objective function is only in terms of one variable. And since we solved for y up above, let's go ahead and solve for x in this case. So x is going to equal 100 minus y. So I'm going to plug 100 minus y right on in for x in my objective function. So my product P is going to be equal to 100 minus y times y. Because I took that 100 minus y and plugged it right on in for x, so now my function is in terms of just y. So my P of y is equal to distributing that y through, 100y minus y squared. And remember, what am I trying to do? I'm trying to maximize this product. So I'm going to take the derivative and set it equal to 0 to find when my function has a minimum or a maximum. So when I take this derivative, I'm going to get 100 minus 2y. Now when I set this equal to 0, how do I know if I'm getting a maximum or a minimum? 100 minus 2y is a linear equation, so I'm only going to have one value that makes this equal 0. And because when I take the second derivative, I get a negative 2, I know that I'm concave down at that point, so I do indeed have a maximum. So solving for when my derivative equals 0, I'll get that 100 equals 2y. Dividing both sides by 2 in turn will tell me that 50 is equal to y. So I know that one number is 50. What's that other number going to be? Well, my other number was x, and I have some equation that x equals something minus y. So I'm going to say that x equals 100 minus 50. So x is also 50. So my two numbers, x and y, are both 50. They sum together to equal 100, and they have a maximum product. 50 times 50 is going to be 2,500. If I tried to use any other number, let's say 49 and 51, right? 49 plus 51 equals 100. What happens when we take the product of that? Well, if we know the product of 50 times 50 is 2,500, even if we go one lower and one greater for each of my individual numbers, 49 times 51 is going to equal 2,499. So not quite that 2,500. This is definitely the maximum. Moving on to the second page, we're going to go on to example 3. In example 3, a picture is going to be super helpful. It says that there's a piece of cardboard that's 12 inches by 18 inches. So we have some rectangular cardboard that's 12 inches by 18 inches. I'll go ahead and start drawing this out. Here's our 12-inch side, and here's our 18-inch side. The plan is to cut a square out of each corner and fold the sides to make an open top box. So if we're cutting a square out of each corner, I'll go ahead and do this in yellow so that you can see those cuts. So if we cut those out, you can see, I'll go ahead and do a perforated line, how those would nicely fold up along those dashed lines that I just did. Those two sides would fold in and the other two sides would fold in to make an open topped box. It says, what are the final dimensions that will maximize the volume, and what is that volume? So we're trying to maximize volume. Volume is our objective function. So writing out our objective function, volume is going to equal length times width times height. So volume equals length times width times height. That's what we're trying to maximize, that volume. What is our length? What is our width? And what exactly is our height? We know that we're cutting squares out of each corner. And in order to make that box nice and symmetrical, we need to cut the same squares out of each corner. And in a square, all sides are the same. So I just need to pick a variable, let's say x, to name the sides of the square. So this side of the square is x, so is this side. Here's our x and x, 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 and then x and x. So you can see the sides of each of those squares that we cut out are x. And when we fold that up, we're really looking at a box that has a length to here, a width to here, and then the height, when we fold that up, is going to be x. That is our height. When we fold up that cut out side, that height is x. So we know that our height is x, but what exactly is our length? Well, look, we took that 18 and we took out 2x. We removed this x, and that x there to get our total length, because when we cut that out, we shorten the length of our box. So our length L is actually equal to, let me go ahead and write this out, h is equal to x. Our length L is equal to 18 minus 2 of those x's, because here was x here, and here was x here. Taking that away from 18 is 18 minus 2x. And then also our width W is going to be same concept. It originally was 12 inches, but we took out x and x to shorten that, so it's going to be 12 minus 2x. So if these are essentially if you want to think about them as constraint equations, each of them are in terms of x, so I'm going to plug that right on into my volume formula. Volume is going to equal, my length is 18 minus 2x, my width is 12 minus 2x, and my height is x. That's my length times width times height. Is my objective function in terms of one variable? Yeah, it is. It's just in terms of x. I rewrote L in terms of x, W in terms of x, and H is x. So now we can go ahead, distribute this out, take the derivative, and set it equal to 0. So distributing this out to simplify down to make taking the derivative easier, I have 18 times 12, which is 216, and then I'm going to be subtracting 2x times 18, and then subtracting 2x times 12, which is going to be minus 36x, and then minus 24x, which is going to give me minus 60x, and then negative 2x times negative 2x is going to be plus 4x squared. And that is all multiplied to x. So this is my length times width, and this is multiplied by height. Let's finish distributing that out to get 216x minus 60x squared plus 4x cubed. So that's my volume, v of x. My function volume is in terms of one variable, x. In order to find that maximum volume, I need to take the derivative. So I'm going to have that volume, that derivative of volume, is going to be equal to 216 minus 120x plus 12x squared. So if this is the derivative of my volume, I set it equal to 0 to find my maximum and minimum values. But remember, I want to maximize this, so I'm going to look for that value that maximizes that volume. So setting this equal to 0, each of my terms are divisible by 12, so I'll divide both sides by 12 to get that. Well, first of all, 12x squared divided by 12 is going to be x squared, minus 120x divided by 12 is a 10x, and then I'm going to be adding that to 216 divided by 12 is 18, and that's all equal to 0. Writing it this way, I'll be able to factor my equation to find what makes this 0. Actually, it doesn't look like we're going to be able to factor this, but that's okay. What other method can we use? Quadratic formula, right? Opposite of b, so x is going to be equal to 10 plus or minus the square root of b squared, which b is negative 10, so negative 10 squared is 100, minus 4 times a, which is 1, times c, which is 18, and that's all over 2 times a, 2 times 1. So x is going to be equal to 10 plus or minus 4 times 18 is 72. 100 minus 72 is going to give us 28. So this is going to be 10 plus or minus the square root of 28 all over 2. So we're going to get, you can see, two separate values because we're adding and subtracting that square root of 28. So that means that x is going to be either, well, splitting this fraction up, 10 over 2 is going to be 5, and then I'll have 5 plus square root of 28 over 2, which square root of 28 over 2 might even be easier to think of as 28 is 4 times 7, so we can take out that greatest perfect square of 4 to get 2 root 7. So then 2 divided by 2 is simply 1, so we have 5 plus or minus root 7. And because it's kind of hard to envision exactly what root 7 is, we know that it's between 2 and 3, because the square root of 4 is 2 and the square root of 9 is 3. We know it's between there, but if I was to enter this into a calculator, root 7 is approximately 2.645, which I'm going to round this to 2.65. So if we have 5 plus 2.65, we're going to be at 7.65, and if we have 5 minus 2.65, we're going to be at 2.35. So x is either 7 65/100ths or it's 2 35/100ths. And remember, we're trying to maximize this volume. So which one is it? Do they both give us a maximum volume? Well, let's think, because remember, if we take the second derivative, and for those x values, if the second derivative is positive, that means we're concave up and at a minimum. If that second derivative is negative, that means we're maximum. So let's try to figure out which one is the maximum. Another way to do this is, especially if you have a calculator, feel free to plug those numbers back into the original volume formula to see which one's going to give you the greatest value. When it gives you the greatest value, that's going to be your maximum. But to practice taking derivatives, I'm going to find the second derivative of x. So that's going to be, well, 216 goes to 0. Negative 120x becomes negative 120, and then I'm going to be adding 12x squared. That derivative is 24x. So if I was to plug my x value of 7.65 in, when I plug 7.65 in, I'm going to get a number that's roughly around 180, and negative 120 plus a positive 180 is going to give me a positive second derivative. Positive second derivative means I'm concave up, so 7.65 is actually going to be a minimum. So let's look at 2.35. When I plug that 2.35 in for x, even if I round, that's going to be a negative 120 plus, let's say, around a positive 48 if I round it to 2, which is going to give me a negative second derivative. So I know at 2.35, my second derivative is negative, therefore I'm concave down, and I'm at a maximum. So x equals 2.35 is going to be the value I'm going to use to maximize my volume. So we need to first see what are the final dimensions, and if x is equal to 2.35, my height h is x, so height is 2.35 inches. My length L, that's going to be 18 minus 2 times 2.35, which gives me 13.3 inches. And then my width is going to be 12 minus 2 times 2.35, which is going to give me 7.3 inches. So those are my final dimensions of my box. And I also need to find what that volume is. So I'll just multiply length times width times height to get my total volume. So my volume V is going to be length of 13.3 inches times width 7.3 inches times height of 2.35 inches. Multiplying those all together is going to give me 228 point rounding to 1/6, and that's inches cubed. So again, I found my objective function. I used my constraints to write my objective function in terms of one variable, and then I took the derivative of that objective function and set it equal to 0. And remember, when you set the derivative equal to 0, those are your critical points. So mins and maxes are when the derivative equals 0. So if you're trying to maximize, you need to make sure that you use the correct value that maximizes. And you can double check that by using the second derivative, or you can plug it back into your original function to see which one gives you a greater value. Let's move on to example 4. Our last example on this worksheet. It says you enter a race that starts on the beach and ends at a lighthouse that's on an island. The lighthouse is exactly 4 miles down the shore from the finish line and 1 mile across the water. So if I was to draw this picture, I'll have my beach in yellow, I'll have my starting line for the race, and then I'll draw my little island out here that has the lighthouse on it. Again, we know that this distance along the shore is 4 miles. And we know that this distance, they tell us, is 1 mile. So 4 miles to get to some point, and then exactly 1 mile directly out to that lighthouse right across the water. So if you can run 7 miles per hour and swim 3 miles per hour, at what point along this beach should you jump in the water and start swimming? So if we were to think about this, here we are running along. What point do we stop and jump in and start swimming for the lighthouse? We need to figure out that value, how far we're running. We'll call that x. Now, this is a race, so we're going to want to minimize the time spent. So now that we have our picture, we want to minimize that time that we spent. We're going to take the derivative of our objective function and set it equal to 0 and find that minimum value. But what exactly is our objective function? Well, our objective function is, so what exactly is our objective function? We know that our goal is to minimize time, because if this is a race, we want to make it as quick as possible. And what we're given distances, and we're also given rates that we can accomplish different tasks. So if we know that the length of the shore is 4 miles, we need to figure out that point along the beach that we should start swimming in order to minimize our time. So essentially, however far we go in this x, that distance will take our rate that we can run, that 7 miles per hour, and divide it by our distance to get that time it took us to get to that point. But then we also need to know that length that we swam and divide that by the rate to get the total amount of time. And that's what we're trying to minimize. So I'm going to say my total time t is going to equal, well, however far I run, if I divide that by the rate I run, I'm going to get the total time it took me to run. So if x is the point where I start jumping in the water and swimming, I'm going to divide that by 7 miles per hour. Because you can see that if I ran x miles, then I divide that by 7 miles per hour, that's going to give me how many hours I essentially ran. But that's only my length that I'm running. I also need to add that to the length that I swam and figure out the time that I swam. So I need to figure out this distance here. So if we know this distance is x, we know that this forms a right triangle where this length is 1. What is this length here? Because then I can just use the Pythagorean theorem. Well, that length here is 4 minus x. Whatever distance we ran, we're going to take away that distance, and that's going to be what's left along the shore. But that's that point we jump into the water, so we're going to use the Pythagorean theorem to figure out that length of the triangle. So 1 squared plus 4 minus x squared equals L squared. Solving for L, we'll just take the square root of both sides. So I know that this length here is the square root of 1 squared is 1. So that's 1 plus 4 minus x, that quantity squared. So whatever that is my distance I swam. 1 plus 4 minus x squared, the square root of that, that's how many miles I swam, and that's all over my time it took me to swim, which was 3 miles per hour. So if I minimize my time, I'm going to be able to figure out that point x when I should jump into the water. And if you notice, using these constraints over here that I formed in my picture, I have my objective function t just in terms of x. So let's go ahead and make this a little neater. I'm going to drop my labels for now because you notice miles will cancel out to leave me with just hours. So my time I know is in terms of hours and my distances are in terms of miles. So I'll go ahead and drop my labels and write that my objective function t of x is equal to, this is going to be x over 7 plus 1/3 times the square root of 1 plus 4 minus x squared. Now what I need to do is I need to minimize the time it's going to take me to race. So I need to find that point X where I'm going to jump in and start swimming to get the least amount of time spent racing. So I'm going to take the derivative of my time function to figure out those critical points. And I may have a couple critical points. I may see when my time is at a maximum, and I may have a time that's at a minimum. And I want that minimum time. So I'm going to do t prime of x, and that's going to be equal to the derivative of x over 7 is 1 over 7, plus, here I'm going to need to do a little bit of chain rule. So I'll leave my constant out in front, and then I'll multiply that by 1/2 times 1 plus 4 minus x squared to the negative 1/2. And then I need to multiply by the derivative of my inside, which 1 goes to 0, but the derivative of 4 minus x squared is a chain rule in itself. So that's going to be, again, bringing down the exponent, 2 times 4 minus x, and that's all raised to the first now when I decrease that exponent by 1, but then I still have to multiply by that derivative of that final inside, 4 minus x, which is multiplied by a negative 1. So again, remembering that chain rule, I first had to deal with the square root, dropping that 1/2 down in front, then decreasing my exponent by 1, and then my next innermost function, I had that squared, and then finally multiplying by the derivative of my innermost function. So simplifying this down, my t prime of x is going to equal 1/7 plus, or really, because I have all of this multiplied by a negative 1, so this is going to be 1/7 minus, what's left in my numerator is 2 times 4 minus x, which is going to be 8 minus 2x, all over 1/3 times 1/2 is that 1/6, so all over 6 times the square root of 1 plus 4 minus x squared. Now remember, I'm trying to figure out when this derivative is equal to 0. So if I set this equal to 0, I'm going to attempt to solve. So I'm going to have that 1/7 is equal to 8 minus 2x all over 6 times the square root of 1 plus 4 minus x, that quantity squared. Now this looks a little messy, so I'm going to try to simplify everything down. First, I'll start by multiplying both sides by 6. So when I do that, this 6 will get canceled out, and I'll have a 6 in my numerator over here. So now I have 6/7 is equal to 8 minus 2x times the square root of 1 plus 4 minus x squared. And you know what? Let's go ahead and rewrite this 8 minus 2x. Let's put it back as 2 times 4 minus x. That way I can also get rid of this 2 by dividing both sides by 2. And when I do that, when I divide both sides by 2, I'll now get 6 over 7 times 2, which is 6 over 14 on my left-hand side. And if I want to, I can simplify that down. Since both are divisible by 2, this is going to be 3/7. So I have that 3/7 is equal to 4 minus x over the square root of 1 plus 4 minus x squared. So this is looking a little complicated to solve. I don't like having that radical in my denominator, so what I'm going to do is I'm just going to square everything and see if that gets me anywhere. So when I square both sides, I'm going to get that 9 over 49 is equal to 4 minus x squared all over 1 plus 4 minus x, that quantity squared. Because the square root, when I square that, that goes away. So now I don't have to deal with that radical, although this still doesn't look quite simplified down because I still have this fairly large denominator. But think about if I cross multiplied. If I multiplied 9 to that and then 49 to my 4 minus x squared, but then I divided 4 minus x squared and divided by 9, essentially I'm going to flip all of my fractions. So I'm going to have that 49 over 9 is equal to 1 plus 4 minus x squared all over 4 minus x squared. And by doing this, this is going to allow me to split this fraction up. So I'm going to have 49 over 9 equals 1 over 4 minus x squared plus 4 minus x, that quantity squared, over 4 minus x, that quantity squared. You can see that this will simply go to 1, and then I'll subtract it. So I'm going to get 49 over 9 minus 1 equals 1 over 4 minus x, that quantity squared. So I'm getting closer. This is simplifying down now, but I don't want to have 49 over 9 minus 1. I'm going to do 49 over 9 minus 9 over 9, because if I do that, I'll be able to get a common denominator. So I'll get 40 over 9 is going to be equal to 1 over 4 minus x, that quantity squared. Now again, if I flip those fractions one more time, essentially cross multiplying and then dividing by that 40, because on one side I'll have 9 times 1, which is 9. The other side I'll have 40 times 4 minus x squared. So if I divide by that 40, I'll get 4 minus x, that quantity squared, is equal to 9 over 40. Now I'm starting to get closer. I can either distribute this binomial through, or I know that 4 minus x squared is going to be equal to 9 over 40. So I'm going to see when 4 minus x, when does that equal the square root of 9 over 40? The square root of 9 over 40 is going to be 3 over the square root of 40. And because I took the square root, that's going to be plus or minus. So when I subtract 4, I'm going to get that negative x is going to equal plus or minus 3 over root 40 minus 4. So I'm going to get a negative 4 plus 3 over root 40, or negative 4 minus 3 over root 40 for negative x. So when I do this out, I'm going to get that negative x either equals if I take the positive, and this comes out to be about 0.47, if I take positive 0.47 and subtract 4, I'm going to get a negative 3.53, and if I take that negative 0.47 and subtract 4, I'm going to get a negative 4.47. So that means that x is going to either be a positive 3.53 or a positive 4.47. But think about that. X is that distance. Does it make sense for x to be a positive 4.47? If I ran 4.47 miles, I would run past the lighthouse. That doesn't make any sense. So my x is going to be that value of not 4.47, but 3.53. So I'm going to run 3.53 miles down the beach before I jump in the water and begin to swim. So if x is equal to 3.53 miles, that's the point where I jump into the ocean and start to swim. So if I know that my x is 3.53 miles, how far do I actually wind up swimming? I know this isn't necessarily the question, but let's figure it out. How far I wind up swimming is going to be the square root of 1 plus 4 minus 3.53 squared. That's going to be how far I wind up swimming, which 4 minus 3.53 is going to be 0.47. When I square that and add it to 1, I'm going to get 1.2209. And if I take the square root of that, I'm going to get approximately 1.10. So I'm going to wind up swimming about 1.10 miles. So if I run 3.53 miles and I swim 1.10 miles, how much time do you think it's going to take me to complete this race? Well, I can just plug this right back on into my objective function for time to figure out that total time. So I'm going to take my 3.53 and divide it by 7 to get 0.50. So I ran about 0.5 hours, and then I would swim about, well, taking that distance 1.10 and dividing it by 3, because that's how long it takes me to swim, 3 miles per hour. I'll get that I swam about 0.36 hours or 0.37 hours. So if I run for 0.5 hours and swim for 0.37 hours, the race should take me 0.87 hours, which in terms of minutes, because it might be easier to think of that as minutes, that's going to take me about 52 minutes and 12 seconds to complete the race, which is indeed shorter than if I just ran 4 miles and then swam 1 mile. If I ran the whole length of the beach and then jumped in the water at that point and swam, think about it. 4 divided by 7 is going to be 0.57, so then I would be running for 0.57 and then swimming for 0.33. 0.57 plus 0.33 is going to be 0.9, which is greater than that 0.87 hours total that I get when I jump in the water at 3.53 miles in. Now I understand that this was a longer problem, and that was mostly because of the algebra. So if you're able to use technology, it might be easier just to find the roots of this using technology. And it also might have been easier to simplify my problem down a little bit more at the beginning. However, working through that algebra, we still got our answer, and in this case we got 2 separate x values, so we had to decide which x value made sense for our problem. Which one clearly did. We did not want to run past the lighthouse and then have to backtrack swimming. So jumping in the water right before the lighthouse and swimming gave us our minimum amount of time to run that race. And with that, we wrap up these optimization problems. We started out with a few easier ones and then jumped into some more complicated ones. And I find that for the more complicated ones, a picture really helps to get all the information and then use that in order to write your objective function. But remember, our goal is, if we're minimizing or maximizing our objective function, we need to find the critical points. So eventually we're going to take the derivative of our objective function and set it equal to 0. In order to take that derivative and set it equal to 0, we want it in terms of how many variables? 1 variable. So once we've set our objective function in terms of 1 variable using the constraints, then we take the derivative and set it equal to 0 to find those critical points. And then we decide which value we're going to use. Are we trying to maximize or are we trying to minimize? Sometimes setting it equal to 0 is only going to give us 1 value. Sometimes we might get multiple values and then have to decide from there. But then, once we get that value, we'll use that to answer any questions for our problem. But again, the important step is writing that objective function in terms of 1 variable, taking the derivative and setting it equal to 0. From there, you just have to think about it logically to decide what to use. So go ahead, get some extra practice in before continuing on to the next video. And until then, good luck with your online learning.